In this video, we're going to talk about infinite limits. So far, all of the limits that we've taken a look at were finite limits. They came out to be numbers, right? And so when we said that the limit existed, the limit came out to be a definite number. So before we get started on this, let's take a look at just a numerical experiment. So just pick any random non-zero real number. So I'll just pick something like 17, just any random number, and what we're going to do is repeatedly divide that number by numbers that get closer and closer to zero. So I'm just going to do that in Desmos over here. So I'm just going to take 17 and divide it by numbers that get pretty small. And here you can see 17 divided by 0.1 is 170. Right, when I divide 17 by 0.01, I get 1700. And the closer the number on the bottom gets to zero, the larger that quotient is going to be. The result becomes huge there. All right, so you might think, well, maybe that's because I specific to 17, the number that I picked, but it's not really. You may say, well, what if I took a really small number on top also? That's pretty small, right? And so that would give you a small number when you did the division, but the closer and closer that bottom number gets to zero, the larger and larger the division becomes. So what happens as to the quotient or the division, the result, right? As you divide by numbers that get closer and closer to zero, well, that value gets larger and larger in this case. And do the results of the experiment depend on the number you picked? Well, if I pick any positive number, then the answer is no. Here, I'm going to have that same behavior that I had here. The closer and closer that number gets to zero, the larger and larger that division is going to be. If I did pick a negative number on top here to begin with, then I will get a slightly different behavior, right? The numbers will actually get smaller and smaller, and by smaller and smaller, right, what I mean is that in absolute value they are large, right? So if I disregard the sign of the number, then that's a large number, but it has a negative sign in front, right? Those numbers technically are small numbers, right? They are far to the left on the number line. So when I say smaller and smaller, I don't necessarily mean closer and closer to zero. What I mean is that in absolute value they are big, but they are negative here. Okay? So if you have a negative number on top, what will happen is the numbers will get smaller and smaller, and if I have any positive number on top, the numbers will get bigger and bigger. All right, so whenever we have that sort of behavior in the limit, what we are going to say is that one of two things. So first here you see the definition of the limit as x going to a of f of x being infinity. Okay, that's going to mean a couple of things. That's going to mean, number one, that the limit does not exist. That is always a little bit tricky when people are first learning this because people will say, well, yeah, the limit exists. It comes out to be infinity. But if you read any math textbook or like the limit laws, right, when they say that the limit does not exist, or when the limit exists, what they mean is that the limit comes out to be a specific number. So in other words, the limit exists, it gets closer, the y values get closer and closer to 15, so to a specific number. Here we can't say that in that sort of behavior that we've looked at just a second ago. The numbers get larger and larger, so they don't get closer to any fixed number, right? They get closer, they get larger and larger the farther we go. So if you take x values, they get closer and closer to a specific number, and you look at the y values and they get larger and larger, then what we would say is the limit as x goes to a of f of x is positive infinity. That means the limit doesn't exist, but it doesn't exist in a special way in that the y values get bigger and bigger the closer and closer I get to a. Likewise, the other situation where we had really small values, so in other words, again, large in absolute value, but with a negative sign in front, we would say that the limit as x goes to a of f of x equals negative infinity. So here again, that means two things. That means number one, that the limit does not exist, right? In the sense that mathematicians usually use that. That is, it doesn't get closer to any fixed single number, but it gets smaller and smaller. The y values get smaller and smaller the closer we get, the x values get to this number a here. Okay? So that's sort of the two behaviors that we saw in the previous numerical experiment. There are similar definitions, right, for the limit as x goes to a from the left of being infinity and the limit as x goes to a from the right being infinity, and all the other various combinations there, right, with the obvious interpretation that the limit from the left is we're just looking at the x values from the left, and the limit from the right being that we're only looking at the x values that are on the right of a here. So in all cases, right, the fact that the limit is infinity or minus infinity, again, means that those limits don't exist, right? It's just that they don't exist in a special way, and that special way is they either get bigger, the y values get bigger and bigger in the case of infinity, or they get smaller and smaller in the case of minus infinity. Okay? All right, so let's take a look at our first example here. We want the limit as x goes to 0 from the right of 1 over x, the limit as x goes to 0 of 1 over x, and the limit as x goes to 0 of 1 over x, the two-sided limit. Okay, so we're just going to do that numerically, the table at first, and then later on we are going to switch over to the analytic point of view. So first off here is my function here in Desmos, f of x equals 1 over x, and I've gone ahead and made the table right here. Here I'm taking the limit as x goes to 0 from the right, right? So these x values are getting closer and closer to 0. They are all on the right of 0. In other words, they're bigger than 0. And here are their corresponding y values, right? And so what we can see is that those y values are getting bigger and bigger in this case. Okay? So what we would say about the limit as x goes to 0 from the right of 1 over x, it's going to be equal to positive infinity. So this one's equal to positive infinity. Over here we have a table where the values of x are getting closer and closer to 0, but all of these numbers are to the left of 0. So this is looking at the limit as x goes to 0 from the left numerically. And we can see when we plug those values in, right, the resulting y values are getting smaller and smaller. Again, by smaller and smaller, I mean in absolute value they're large, right, if I ignore the sign of the number, but they're all negative. So, okay. So for this second part here, we would say the limit as x goes to 0 from the left of 1 over x equals negative infinity on this one. So the second one is negative infinity. For the two-sided limit, we would have to decide by looking at both the one-sided limits here. Since the limit as x goes to 0 from the right of 1 over x was positive infinity, and the limit as x goes to 0 from the left of 1 over x was negative infinity, then the best that we can say here about this limit is that it does not exist. So the two-sided limit doesn't exist. We can't say that it's infinity because, well, from the left it's going to negative infinity. And we can't say that it comes out to be negative infinity because from the right it's going to positive infinity. So if both the one-sided limits are infinity, then we could have said that this one was infinity, or if they're both negative infinity, then we could have said that this is negative infinity, the two-sided limit that is. But on these, since they're doing different behaviors on the right and on the left, the best that you can say about the two-sided limit is that it is that it does not exist. Okay. Let's take a look at the graph of 1 over x, and you can kind of see that behavior reflected in here. So here, what's happening as the values of x get closer and closer to 0. Well, here you can see that this one is from this part of the table right here at 1, 1. Then I move a little closer at 0.1. It will be 10, the y value. And the closer and closer I get to 0, those y values start getting really big the closer and closer I get to 0. Over on the left-hand side, if I can look at the points in the table here. See, -1 is right here, and then -0.1 and -10 is right here. So as I come in from the left and get closer and closer to 0 from the left, the y values are getting smaller and smaller here. So it was positive infinity here and negative infinity over here. As you can see, that this graph has a vertical asymptote here at 0, and the limit being infinity or minus infinity at a number right indicates that it will have a vertical asymptote at that number. But we will talk a little bit more about that in a later video. Okay, so what we really want is to develop some analytic approach to taking these limits, right? And instead of looking at a table of values or looking at the graph, how would we analyze a limit without doing either of those two things? So if you notice in the previous example, right, if you plugged in the number that at which you were taking the limit, right, into 1 over x, so in other words, if I plugged in a 0 here, or tried to, right, I'd get a meaningless expression, but I would get a non-zero on top. Here it's a positive one, and here I would get 0 on the bottom. And so that's a common thing that happens with all of these with all of these infinite limits here, or at least the ones that we'll take a look at. So if I have a non-zero number divided by 0, that's a mathematically meaningless expression, right? But it will give us some information about what the limit is, right? It will tell us that the limit is either infinity, minus infinity, or does not exist. And we saw all three of those cases when we looked at the 1 over x function. The only thing that you would have to do in a particular problem is to determine which of those three answers is correct. So, and I'll show you how to do that in a future video. So the theorem that we have about the non-zero over 0 case is that the limit as x goes to, if the limit as x goes to a of f of x is L, where L is not equal to 0, and the limit as x goes to a of g of x is 0, right? And I look at the quotient of that, right, the division of that. So the top is going to be a non-zero limit, and the bottom is going to wind up to be 0. Then if I look at the limit of f divided by g, there's only 3 possibilities. It's either infinity, minus infinity, or does not exist. So that's a lot better than the 0 over 0 case that we took a look at previously, because in the 0 over 0 case, we really, just because we got 0 over 0 when we plugged in, that meant you can't really take or decide anything based on just the fact that you have 0 over 0. The limit still could come out to be anything, and that's because 0 over 0 is an indeterminate form. If you plug in to a function and you get a non-zero over 0, then you can make a conclusion. At least you can narrow it down to 3 possibilities, that either the limit is infinity, negative infinity, or does not exist. So in the examples that we will do after this, I'll show you exactly how you would go about narrowing down the possibility to one of those 3.